Good afternoon and welcome. My name is Marissa Bluestein. I'm an Assistant Director at the Quattrone Center for the Fair Administration of Justice at the University of Pennsylvania Carey Law School. We host these monthly training webinars for attorneys in post-conviction litigation and investigation practices as a training program funded through the Bureau of Justice Assistance. This month we are concluding our forensics section for the year with Dr. Jeff Salyards, who's been talking with us about understanding known and potential error rates. This month, how do we apply those specifically to tool marks and firearms evidence programs. So I will remind everybody, if you have questions, please put them in the chat. We'll be happy to watch, and we'll save some time afterwards as well for questions. Now, Jeff, you can take my file off and take yours.
I appreciate the kind introduction. Let's see if I can figure this out.
Keeping it short so we can get right to the program.
Okay, did that go to a slideshow view?
Not yet. It's in the... Yep, there we go.
Okay. All right, very good. So I hope many of you were with us last time. We talked about the general concept of establishing an error rate and accuracy and reliability and validity studies. We'll review that ever so slightly today just to keep us focused. But really, we want to talk about firearms and tool marks evidence. And so we'll delve into what is sort of the known or potential error rate, and then what are some ways that the firearms and tool marks community, what do they do well and what could they do better? How are they maybe creating distractions when they testify? So I actually gave part of these slides at an AFTI meeting in 2024 in Anchorage, Alaska. And for those movie aficionados with enough gray hair, you might remember Jaws. I started with this slide because I have worked in this space as a consultant and have testified often for the defense against some firearms experts. And so they weren't necessarily thrilled to see me when I showed up at AFTI. So I'm reminded of Hooper here saying, I'm just saying this might not be the shark. I don't really want to get beaten up over it. And I reminded him that when I testify, of the experts in this space, I'm probably the most gentle. There are some that really believe this is along the lines of bite marks and that it's totally witchcraft. I'm not one of those. But I do think that the false positive error rate is could be higher than reported. And we'll talk in more detail today. That's largely about confusion around how we're going to handle inconclusive results in these validation studies. And then reproducibility, when two examiners look at the same thing, there's one study in particular that shows we're not doing as well with that as we should, and that's a troubling metric, so we need to talk about that. And then even the best studies, we'll talk about good and bad ones today, even the best ones have some inherent weaknesses, some things that even if you gave me $1 million and infinite time to do the study, I still might have to just adopt and deal with some of these weaknesses. So we'll talk about what that does to the measured accuracy, what that does to your error rates. It doesn't make them just nonsense, but you do have to deal with it. So the first thing to probably address is this AFTI theory of identification. And the reason that I throw this up here...
Jeff, I'm sorry, I'm interrupting. If you could just explain to us what AFTI stands for.
Oh, thank you. The AFTI is the Association of Firearms and Tool Marks Examiners. So it's the professional organization where most of the firearms and tool marks examiners sort of reside and get their training, and they have a yearly conference. They have a theory of identification. They also have a range of conclusions, and then they have a host of various white papers, documents. If there's some piece of legislation or some court case that affects firearms and tool marks, they might comment on it. So this AFTI theory of identification, I have not encountered a lab in the United States and even internationally that does not adopt this and base their training on this. And so this is both a good and a bad thing. The good thing is, anytime someone writes something down where there was nothing previously, that's a good thing, right? It makes you declare what you believe in. The challenges with this theory is it creates a mindset in the firearms and tool marks community that begins a departure from what I would call the mainstream scientific community. And so each one of these points has a few kind of sharp sticks that need to be avoided. The first is this term sufficient agreement. That's an invented term by the AFTI community. the larger statistics community, physical science community, we don't talk about sufficient agreement. Now, you're allowed to invent terms in science, create your own lexicon, but then the burden's on you to describe and define very carefully what do you mean by that. And so they take a step to do that, but they refer to it as significant duplication of random tool marks. And that raises a second issue because significant is a word that we use in physical science and statistics. And we've already got a really clear definition of that. It's around like what am I seeing? And what are the chances that I would see this by accident? What if there's no correlation between the thing that I think is correlated? I'm flipping coins. I flip five in a row. Do I have a magic coin? Five heads in a row, or did that just happen by accident? So significance is about comparing those two conditions. And so they invoke that term here, but then they use it not in the traditional way. So that's its own challenge. They take a step in the right direction by saying specifically we're going to look at the relative height and depth and width and curvature of spatial surfaces and individual peaks. But then they miss the boat in that everywhere else in science, if I talk about a height or a width or a depth, I have to break out a ruler, right? I mean, now I'm measuring something that can be in meters or centimeters or nanometers, and then there would be standards about how do those numbers have to compare. So they begin to take a step towards something quantitative, but then they kind of lose the focus of that. And then further in here, they create an interesting situation. So they now say the agreement is significant when the agreement and the individual characteristics exceeds the best agreement demonstrated between tool marks that are known to have been produced by different source tools. So let's think about what that means. The examiner is supposed to be, I'm looking at tool marks and I go, these are really similar. And then I'm going to remember the the non-matching pair that I've seen in my history that was the most similar, even though I knew they were non-matching. Does this thing have more agreement than that? And so I understand why they would invoke this. I think they're trying to say, hey, be really careful if you're going to call something a match. And that's a good thing. But the bad part of this is it creates a situation that's untenable for examiners and inherently inconsistent. So what do I mean by that? Human beings are not very good databases, right? That's why we have, actual databases and computers, and that's why we have white pages for our phone numbers, and we don't remember things like that very well. But the second reason is if we set that aside and say, hey, let's say I remember perfectly what I've looked at, and Marissa remembers perfectly what she's looked at, then that would mean inherently we would have two different thresholds for declaring something a match, right? And that becomes problematic in science. You don't want a method where if you look at it, you get one answer, but if I look at it, I'm applying a different threshold and I get a different answer. So I think unknowingly they built in this inherent contradiction there. And then they unfortunately use some language which I don't think is scientifically defensible at all, where they say the statement that sufficient agreement exists, and then they go on further to describe that as the likelihood another tool could have made the mark is so remote as to be considered a practical impossibility. And so I think that's difficult for anyone to square. What do we mean by practical impossibility? It sure smacks of a zero error rate. It sure smacks of like this is infallible. And it's not. So even the error rate studies that we'll talk about shown in their best light, the error rate's around 1 or 2%. That's a far cry from practical impossibility. Imagine in the DNA world, that would be like them saying you have a random match profile of 1 in 100, right? Most of us will go, wow, that's a really low number. So if that's what the data are showing, certainly doesn't indicate that it's witchcraft, but it does not support language like that. So that's important, I think, to lay the backdrop of if I'm a new firearms and tool marks examiner, I get taught this in an almost very religious way. This is sort of doctrine. This gets ingrained. Many training programs have them memorize this. And so I think that creates challenges when those examiners mature and start thinking about maybe planning studies. They're maybe thinking about it already. They're off on the wrong foot, maybe. So the history of farms and tool marks, I think I shared this slide last time, but we have all the way back sort of pre-2005, there's language like there's a wealth of literature that demonstrates the validity of firearms and tool marks. And I remember early in my career, I was a special agent with the Air Force OSI all the way back in 1988, visiting the forensics lab for the first time and hearing this. And probably like many judges and lawyers at the time, even defense attorneys at the time, I thought, well, yeah, that makes sense. Of course there is. We wouldn't be doing this if there wasn't a lot of literature supporting it. And I was pretty immature in my own scientific career, so I wouldn't have really known how to interrogate that, where to look, how to read those papers. In 2008, there's an NRC study, not the blue one here, not the one we call the NAS report. This one was called ballistic imaging. And the goal of it wasn't to validate firearms and tool marks examinations. It was looking at a more user-based question, which was, could we have a sort of nationwide database where information is shared freely on shooting cases? But because it was populated by sort of mainstream scientists, they begin to scratch the surface and said, hey, we're looking at your bibliography, and maybe we're just looking in the wrong place, but the validity of these fundamental assumptions of uniqueness and reproducibility has yet to be fully demonstrated. Like we can't find the papers that we think you would need. So they stopped short of that. They didn't say they don't exist. They just said maybe you need to find those and staple them together. Then in 2009, the NES report comes along and is, a wake-up call for a lot of forensic science disciplines. But regarding firearms and tool marks, they say sufficient studies have not been done to understand the reliability and repeatability of these methods. And so there's a brief time before the PCAST report. There's the White House Office of Science and Technology Policy puts together a subcommittee on forensic science. I get to serve on that. I'm actually one of the co-chairs of a research and development working group. And so we created these annotated bibliographies, and it's something I was really proud to be part of. We invited in each forensic science discipline. So for the firearms and tool marks community, we invited in an AFTI representative, and that at the time, something called SWIG Gun, the Scientific Working Group on Firearms and Tool Marks, was up and running. So we invited them in and said, give us your sort of Daubert presentation, your admissibility presentation. And then I had a room full of scientists from around the government, people from NIST and various universities. We created a list of questions and said, if you think you can do those things, we would expect scientific scholarly papers that address these issues. And so they submitted back a bibliography and said, we think these papers answer those questions. And we actually asked them to annotate it. And I think you can find their response still on the AFTI website. I had grand intentions of reading all those articles, putting together task groups, and, if you will, giving them a letter grade. And this group sunsetted before that happened. But the PCAST came along and tackled this, several of these disciplines, and they essentially picked up those annotated bibliographies, and they did read those studies that were being offered by the Firearms and Tool Marks community. And we find that many of these earlier studies were inappropriately designed to assess foundational validity and estimate reliability. And so then they point out, it looks like there's only one study that we think was designed correctly. And that's how I kind of become attached to this firearms and tool marks issue. The study they cite was hosted by the Defense Forensic Science Center, where I was ultimately the executive director. But prior to that, I had served as the chief scientist. And so I had actually commissioned this study. I went out and sought out a guy named Dave Baldwin, who was a chemist working in Ames, outside of Iowa State. He had been around the forensic science community, but was also a very respected mainstream scientist. And so I had several meetings with him of how would we do this right? How would we overcome the limitations of some of these earlier studies? So this was kind of a nice feather to have PCAST say, hey, that one looks like it was done correctly. All right, so that backdrop I think is important. We're going to talk about the M words again. We talked about those in our last session, so I want to remind us. And then I've got three new M words for us. And then we'll jump into sort of the meat of the current validation studies and what are their strengths and weaknesses. And I think we're going to find they even kind of fit in two groups, sort of the so-called pre-PCAST studies and the post-PCAST studies. And then finally, this idea of maybe the way forward for the Firearms and Tool Marks Committee would be to hug the cactus. That's hard for us in forensic science in this more adversarial setting. I'm not encouraged as a forensic scientist to lean into my weaknesses. I'm encouraged to come up with really good rhetoric to deal with cross-examination and put up a strong front. So maybe the way forward would be a more scientific humility and how do we hug that cactus here? All right, so just a brief review. Last time we talked about how we use these words, and I think there's just an important distinction for lawyers and judges mostly that I run into. You'll use the word reliability the same way a mainstream scientist would mean validity, meaning something that can be relied on. For scientists, reliability means something more narrow. It's sometimes called precision, and it includes repeatability and reproducibility, and it doesn't deal directly with do I have the right answer? It just deals with do we get the same answer? If I use the same method, if I step on my scale and it says I weigh 177 pounds and I step back on the scale, does it say I weigh 177 pounds? And if it doesn't, does it say 178 or does it say 243? Right? And you can begin to see the problem before we even get to is that my weight? If it says 177 and then 243 and then 62, you go, I don't know what to do with that, right? That we can't even move on to accuracy. So reliability is that sometimes called precision, repeatability, reproducibility. Reproducibility is a broader term of I step on this scale and maybe now I step on another scale and then I step on a third scale to all three scales agree or three different examiners look at the same evidence. And then accuracy is do I get the right answer? And accuracy, we talked about last time, there's two ways to kind of get a wrong answer, and they are really different flavors, right? So one is this idea we call sensitivity, and that says when you give me a true positive, the sample really is cocaine. These two cartridge cases really do match each other. Am I able to detect that? Do I say, yes, I agree, those match? And specificity, which is when you give me two non-matching samples, do I avoid making the error of saying they do match? Am I able to properly detect, yes, these are non-matching samples?
Jeff, I'm
So,
sorry, I'm interrupting because there's a question in the chat which I missed, and I don't know if you can address it
sure,
now or
yeah.
maybe later. But Chris asked that in the AFTE response to the National Academy of Sciences report, they cite a 1 to 1.3% error rate, but they do not cite the method by which the error is calculated. Is there information available on how the error rate is calculated?
Yeah, that's a great question, and I think around slide 20 to 30, we're gonna go through
Okay,
several of those.
so
So
Chris, hang on
wonderful
to that.
question.
We'll get
Yeah, if
to
you
you.
can put a pin in that, we'll get there. That's a great question. So this slide just reminds us, like, what do we even mean by an error? Um, and that's important because if we think about an examination result, it's often easy to think of it just simply was it right or wrong. But as someone in this space, as someone who used to run a laboratory, that's not how I think about it. I think about it like, was it conforming? Did my examiner do the right things? And if they didn't, they may have made a mistake. They mixed something up. They might have committed malpractice. Maybe they're just not very good at this. They don't understand the spectrum they're looking at. Or maybe it's misconduct, right? They just said, hey, I'm going to call it a non-match. I don't want to write a report. I want to go fishing. Um, Often, firearms and tool marks examiners and all kinds of disciplines, when they're talking about how good their method is, they will tell you about the things they do to guard against non-conforming work. And it's important to draw that distinction because error rates are not about that. Error rates are, I'm going to assume that you conformed. I'm going to assume that you perfectly employed your method. And then that doesn't mean that it's accurate. We hope it's accurate. If it's a good method, it will be pretty accurate. But there will be some false negative errors and some false positive errors. And I take great pains to make a distinction here. I use the word error on this left side and the word mistake on the right side. Often when people are talking about that, they'll sort of conflate those. And certainly in a dictionary, it looks like they mean the same thing. But I think it's important to separate. By an error, we mean this thing that's an inherent weakness, limitation of the method, not something anybody did wrong. So error rate studies are about how good is this are our results when we're over here in that purple box. In PCAST parlance, they talked about foundational validity and validity as applied. And so validity as applied, right, is when I actually use it in my lab, are my examiners conforming? It might have a 1% error rate, but I've got a bad laboratory and we're sloppy and we're lazy and we're bad at this or we're corrupt. And so foundational validity establishes the best you can do. Validity as applied is sort of your mileage may vary, right? Okay, there are a few more M words that we need to talk about. We'll talk about the first two, and maybe at the end we'll come back to this third one. There's a whole interesting debate around the word metrology. So the first one is if you get a firearms and tool marks examiner, especially an old school one, and say, okay, what is firearms and tool marks grounded in? For some reason, and I'm trying hard to find sort of the the primary citation of this. Many of them will say, well, it's based in metallurgy because these are marks in metal. And so it's not, and there's a few reasons I know that. My wearing my other hat, I'm a chemistry professor. There's not a metallurgy textbook I know of that has a chapter on firearms and tool marks examinations, right? Metallurgy is about how do I make metals stronger or more brittle or make them conduct electricity or make them insulate? It's about the properties of metals, right? So that's not really what they're studying. And that's important because if they could properly identify what they're studying, they'd realize that there are other people who study the same thing that aren't doing firearms and tool marks. So some of them take a step closer and say, hey, it's pattern recognition. So when I was at this AFD conference, one of the speakers shortly before me, giving sort of I think, a counter to what I was about to say, said, this is pattern recognition. Human beings have been doing this for thousands of years. If I walk into a building and see my grandmother on the second floor, I know it's her, and I don't have to check all the other floors. I can look at two cartridge cases. If I know they're a match, they're a match. That's my grandmother. And that's a really enticing way to think about it. I think it kind of rings true with us as human beings. Like I know my grandmother, but it's also uh, it's a weaker analogy than I think the firearms and tool marks community realizes, right? Because the courts are already painfully aware of eyewitnesses ain't all that good at recognizing people the second time they see them. That's already been pretty well established. And even though it feels like, sure, I know my grandmother, if I said, well, do you know George Bush? Think about your favorite celebrity and, favorite dozen of them. And every one of us at some point have been in an airport and went, hmm, is that Cheryl Ladd? I wonder if that could be her. And I don't think it is. We've all been at a cocktail party where we think, I think that's Susan we were in a chemistry class together, but I don't want to embarrass myself. I'm not sure if it's her. And we go get a friend to say, hey, would you go introduce yourself so I can overhear if she says her name's Susan? We've all had that happen. So this is not a great thing for them to hang their hat on. And then if we even go to the firearms and tool marks community, Biasotti is one of sort of the godfathers of firearms and tool marks. He was at UC Berkeley, and he publishes, this is back around 1959. He says for bullets fired from different guns, 15 to 20% of the matching lines per land or groove mark are frequently found. So he's saying even when it's a non-match, I see 20% similarity. So what I offered this at this AFD conference was, sure, it's pattern recognition. And you're saying, look, if I see Elvis, I know it's Elvis. But I'm saying, hey, in the typical case, you're at an Elvis convention. And now you're trying to find, is this really Elvis? Now what's your error rate? Now what's your false positive rate? It's more challenging than maybe you realize. So I think what they're really doing is something called signal detection theory. And this is important because there's all kinds of people in this space that have written a lot of really good scholarly things and used a lot of really sophisticated math tools to mature this discipline. But unfortunately, the firearms and tool marks community has been sort of on an island, working really hard to try to solve this, but without the benefit of people who are really deeply in this space. And so the idea would be, if here's the contour of this bullet, and then we can see these bumps, these striations. You can do some mathematical tools that smooths that out, makes it a flat line, and we zoom in, and all those little jagged things become those bumps right there. And now that becomes something that mathematicians and physical scientists like, because that is looks a lot like trigonometry. That's a wavy line, and I can begin to describe that with things like sines and cosines and add them together. And so that's what I've done here on a few slides. Um, so there's one argument, sort of, and I'm sensitive to this, being in laboratory leadership previously, is you're always looking for something that's expedient. And so I'm insisting that they do more sophisticated math. And an examiner says, well, Jeff, why? I mean, everyone can look at the orange line and the blue line and know they're different. We don't need to do, you're solving a problem we don't have. We can just look at this. But then I'd say, okay, well, how about now? Is it just as easy? Or how about now? And how similar does that orange line have to become to the blue line? And then do you want to talk about it in these really qualitative terms of it's a little less similar, it kind of supersedes the amount of similarity I've seen before, or we can just do a correlation coefficient. I can overlay those lines. These could roughly, not perfectly, be thought of as a percentage, right? So I could say, hey, this one looks like it has almost zero overlap. They're completely different. The one in the middle looks like it's got 63% similarity. Once again, I'm running a little fast and loose calling those a percentage, but that's a good first approximation. And you could look at that one and go, well, that one's maybe 96% similar. And so that becomes important because if we really had a number, that's not how I feel about it. That's not how comfortable I feel about how similar I think they are. It's an actual calculated correlation coefficient. If I send the same file to Marissa and say, you look at it, she would do the calculation. I go, yeah, 0.96. I get the same exact number that you got. And then that creates an environment where we can say, all right, what happens if we say that the correlation coefficient has to be above a 0.90 before we call something a match? Then we can say, what does that do to our false positive rate and our false negative rate, right? And we get this more rigorous approach. So related to that, this started with the IAI, the International Association for Identification. They handle mostly fingerprints. In 1973, they put a committee together because they were tired on the stand of lawyers saying, what's the minimum number of minutia that have to match? And they didn't want to declare because they were really worried that if I say that it's got to be at least 7, and then I get a really big case that only has 5 points of minutia, they're going to use that against me. So they were trying to figure out how can we not declare? So we have this quote here that this committee hereby states that no valid basis exists at this time for requiring that a predetermined minimum number of friction-ridge characteristics must be present in two impressions in order to establish a positive identification. This might be one of the greatest sins in forensic science that we've committed because it's wholly untrue, it's completely unscientific, and sadly, they were kind of eloquent with how they worded it, and their audience was hungry to hear it. And so all kinds of disciplines have run with that. And it's almost this Aikido reverse jujitsu move. And I go, hey, you guys need minimums. And they go, no, prove it. You do a study that proves that we need minimums. And that's just antithetical to science. It's the opposite of what we're really trying to establish. So in the larger scientific community, this is captured in this idea of the signal to noise ratio. That concept's probably existed for centuries, but in 1923, right when we're starting to learn about um, like radio signals, we're trying to figure out, is that actually someone's voice trying to come through on the radio or a Morse code trying to come through, or is it just the scratchy noise in the background? So that's when we begin to study it. And then through World War I, World War II, as we begin looking at radar signals, is that just a blip on the radar or is that a hostile aircraft on the radar? So there became a real desire to understand signal to noise. So you could think of it this way. If this were some chromatogram that is going to help me detect drugs, and let's say that cocaine comes out at 200 seconds and fentanyl comes out here at 410 seconds and methamphetamine comes out here at 900 if I went into court and said, yep, I think cocaine's present, we'd all look at that and go, are you sure anything's present? I mean, that just looks like a noisy line. How do you know that that's signal? And so in all branches of physical science, especially analytical chemistry, we come up with this idea that, hey, the signal peak needs to be maybe 3 standard deviations above the noise peak, right? And so you can qualitatively look at it and go, right, the one on the bottom looks much like, okay, those look like real things happening. The one on the top looks like noise. So if you say, hey, we don't require any minimum amount of correspondence, you're inviting your examiners to say, I can live in the noise. I can start looking for the smallest signal that might not be signal and then make some determination from it. Okay, so I offered at the examiners this thought experiment. If we consider two numbers here, many of you are probably familiar with pi. You had to memorize that before you decided you hated math and went to law school, 3.14. There's another number that's around things like exponential growth. So for scientists, this is an equally famous number, E, 2.718. And these numbers have the interesting characteristic that after the decimal point, as near as we can tell, there's people trying to prove this and win a Nobel Prize or a Fields Medal in math. Like, do these eventually truncate or repeat? And so far, it appears they don't. So you imagine if I went to a crime scene and I found just 141592 sitting on the floor, and my task as a math examiner is, did that come from pi or did that come from E? And so since we know those numbers, 3.1415, we all might go, well, I think it comes from pi. But I could ask myself, does that sequence 141592 appear in E anywhere, since E goes on forever and ever? And it turns out if I search the first million digits of E for 141592, it doesn't appear at all. So you might begin to say, well, that kind of supports the idea of a practical impossibility that you're going to find 141592 if it's not in pi. But what if that's not the minimum? I'm allowed to have a smaller sample. I go to another crime scene and there's only 141559. I only have that much of the signal. And it turns out that appears 4 times in the first million digits of E. How about if I just have 1415? That appears 81 times. How about just 141? That appears almost 1,000 times. What if I just had the number 14? That appears 10,000 times. And then, I do get the examiners to say, well, Jeff, you don't understand. Um, this was so special. I've never seen this in my life. This crime scene, I came across this 4-digit sequence and it was 7777. But it turns out that appears 101 times in the first million digits of either one of those numbers, right? So that's where like our humanity interferes with the sort of rigor of mathematics. It doesn't matter that we think that number is special. To the math and the numbers, it just says, no, that's just 4 numbers and they can appear. So why is that important? Because this was a post-conviction case I worked on. The attorney was Chris Fabricant, that you might know of. And he's got the examiners up against the ropes. He was prepared for this. So he says, so you're telling me there's no minimum area required to make an identification? This was in a tool mark case where there was a very, very small amount of tool mark, suspiciously small. So the examiner knows he's on thin ice. If he says, well, yeah, there's a minimum, Chris could say, well, let's start talking about what it is. But the examiner takes the bait and he says, that's correct. There's no minimum. So Chris fires one high and inside and says, so you could make an identification of an area of 1/1,000,000th of an inch? And the examiner says, if the mark were unique enough. Now, I remember 2 things about this. I wanted to, in my mind, real quick, go, what's the nanometers for 1/1,000,000th of an inch?
Oh, at least we got nice
You,
paper
you
there.
and Alfie and Paula are so excited about the paper.
So much better than
There we go.
Sorry about that, just some
No,
bleeding.
that's actually really timely. I'm glad that happened because that plays into this. So I'm sitting in court with my iPhone that I have hard turned off, the little knob on the end. And so I type in 1/1,000,000th of an inch examples. And apparently your iPhone has about 4 different volumes. So in the middle of court, my iPhone loudly says 1/1,000,000th of an inch is 25.4 nanometers. And I'm like, oh my gosh, so I'm trying to turn that down. So 1/1 millionth of an inch that this examiner said that's enough. The coronavirus is 120 nanometers in diameter. He's saying that he can examine things that are 25.4 nanometers. He's saying that, I mean, a red blood cell's 8,000 nanometers. Like, so this is just an absurd statement. So I think at that point you're left saying, perhaps you'd like to rephrase that last answer, right? That's not the place we want to be as examiners, is trying to defend something like that. Okay, so a better answer for minimums would be, so this is once again from Biasotti made this observation, but there's like a striation's like 20 microns wide. And so you would probably want the examiner to say something like, well, at a minimum, I want to compare at least two striations. An average striation is about 20 microns wide. So that means I probably need about 60 microns to look at a couple striations. And as a point of reference, that's about the width of a human hair. And in this case, there were way more striations available, right? That would be way better. This would be even better, though, right? Would be that we actually understand our accuracy and our error rates as a function of how much signal we had. Am I looking at one landing groove mark or two landing groove marks or four striations or seven striations? And so we would probably find, this is called a logistics curve, that there's a certain amount of sample where you say, hey, even though you went from 10 to 20, it's still just not enough. And there's another place where you're like, look, whether I go from 100 to 120, there's more than enough. I'm really, really accurate. It doesn't, but there's a sweet spot, right, where the method begins to work. And this is the kind of stuff that in all forensic science disciplines, but especially firearms and tool marks, we need to understand better, right? So to just declare there's no minimum keeps you from properly investigating what your real error rates are. Okay, let's dig in. I probably talked too long on that. Let's talk about some of the validation studies. So this is a slide that I often encounter or something very similar to it. The AFTI community and SWIG gun before them had something called the Admissibility Resource Kit. And it's a set of PowerPoint slides that often gets kind of recycled and regurgitated at various labs around the country during admissibility hearings. And so they say, here's a list of studies, and then here's the list of error rates, and here's the list of like the number of examiners, and here's whether we think it was an open study or a closed study, or whether it was blind or not blind. And so this is a really problematic slide because there are many studies on here that just are not that good. And then there are many studies over here where they claim that there's such a thing as a zero error rate. They don't report any measurement uncertainty about what they've measured. They don't understand what it really means to have a blind study, and sometimes even what a open or closed study means. So let's delve into kind of a few of those areas. And the other thing they'll say is, we've got all those studies, and look at all the agencies that accept firearms and tool marks. So I like to draw a distinction that like all these agencies are aware of firearms and tool marks. They're not vocal opponents of firearms and tool marks, but they're not vouching for those proclaimed 0% error rates or 1% error rates. And in fact, I think if you just kind of get in Google Scholar and search, there's not general acceptance, or if you want to say that there's general concern, right? Here's over a dozen articles from a range of authors, not writing in response to any instant case, not part of a legal brief, talking broadly about, hey, here are some real limitations in how this community is approaching their craft and how they're establishing their accuracy. So I think it's disingenuous for an examiner to say, oh, there's general acceptance, everything's fine. Like no, it's not. Like there are clearly intelligent voices saying there are some issues here. Okay, so the zero error rate, the Kiesler study is one that I'm going to talk about it, that I put in a special category of sort of the post-PCAST properly designed studies. When he first published his study, he went, okay, of the true exclusions, that means that's the right answer. No examiner set identification. And so he initially in his paper reported a 0 error rate. To his credit, he got with Max Morris out of Iowa State University, a statistician, and Max reminded him, just because you saw 0 errors doesn't mean that there are 0 errors. So this is kind of just a standard concept in probability and statistics. And it goes something like this. If we imagine a swimming pool where I've got it filled with white ping pong balls and every 100th ball is red, we could ask, like, how many ping pong balls could I scoop out of the pool where even though 1 in 100 are red, I might not find a red one? And it turns out that even if that actual red rate, if we call that a false positive rate, was 1%, like 1 in 20 times, I could scoop out 300 balls and not have one red one in there. So most statisticians will use a sample size of 300 as kind of a rule of thumb. And they'll say, if you had a sample size of about 300 and you didn't observe any errors or didn't observe any events, then the actual rate hiding in there still could be as high as 1%, and you just didn't see it. And if you want that confidence interval to be 99%, you've got to go bigger. You'd say, like, I'd have to see about 450. I could get 450 balls out of there, not encounter a red one, and go, you know what, there could still be a red one in there. 1 in every 100 balls might still be red. So that's an important notion that if we were really approaching this as forensic scientists the right way, we would never claim that the error rate's 0. We'd always be looking for this back of the envelope number. All right, we got to remind ourselves what the AFDI range of conclusions is. So they can declare that 2 things match, or they'll call that an identification. They can declare that 2 things are from a different source, or they'll call that an elimination, or they might say it's an inconclusive. Now, this is important. An inconclusive, the way they've written it here, means, hey, everything looks fine with these 2 cartridge cases. I was willing to put them next to each other and look at them, but some things agree and some things disagree, and I just can't make a decision. That's an important distinction between number 4 here, unsuitable or unsuitable, which means maybe it's better to think of with bullets. I've got a shredded bullet from an autopsy, a piece of a jacket casing. I don't see any striations on it. Like, I don't even need to put it on the microscope. I can say it's a bullet, but I can't even tell you what caliber it is. There's nothing to compare. That's important because if you get examiners on the stand and ask them what an inconclusive is, they'll start using unsuitable language. They'll switch back and forth with that when those are really 2 different phenomena. All right, so with that in mind, it creates an interesting situation in these studies. So Dror and Skurich wrote a paper on this, and there are several who have commented. In the study, right, there are kind of just 2 ground state conditions. I went to the firing range and I fired a gun and I got 2 cartridge cases and I know it's from the same gun. And now I got another gun and I fired some cartridge cases and I pair up 2 and I know they're not from the same gun. So the only 2 conditions are, yes, these are same source, or no, these are different source. And so now we've got, what does the participants say? And what we're allowing them to do is use their AFDI range of conclusions. So they could say, hey, it's an identification. They could say, hey, it's an exclusion, but they could also say it's inconclusive. And there's the problem is I don't have 3 ground states. I only have 2. So now we have to say, well, what happens when you say inconclusive? How do we count it? And this is where the real debate starts. The AFDI community says, we think that inconclusives are de facto correct answers. They're always correct answers. What Dror and Skurich would say is you have to figure out a way to make that the right answer, and then it's only right if you call the ground state inconclusive correct, and everything else is incorrect. And so this is going to have some profound effects on the error rates. Now, it might not if they didn't use inconclusive very often, right? If we only used inconclusive 1 or 2% of the time, it would only change my error rate by a percent in either direction. But it turns out, so I want you to think there are really 4 studies that I consider kind of in line with what PCAST said are proper studies. And that's the one they called out, the AIMS 1 study. The Kiesler study, which is actually published in the AFTI journal, but he did a very nice job with it. The so-called Ames-2 study, or Monson study is the primary author, was done with Ames and the FBI. And then one out of Arizona State University by a guy named Giel. Some debate about how to pronounce his name. And so if you look at the reported false positive rates here, they're all like 1%, 2% less than 1%. And that's based on saying every time the examiner says inconclusive, regardless of what the ground truth state is, we're going to say that's the correct answer. There's another measure that we talked about last time we met, this idea of specificity. Specificity is the true negative rate. It says, when you give me a non-matching set of cartridge cases or a non-matching set of bullets, do I successfully tell you back, yes, those are non-matching? And if I don't, then that decrements my specificity. Everywhere else in diagnostic accuracy, the specificity is directly tied to your false positive rate. 100% minus your specificity is your false positive rate. So if we approach this the way the rest of the diagnostic community would, the Ames-1 study, they claim, hey, our error rate was 1, maybe it could be 2% if you kind of go with these using like a confidence interval. But if you say, hey, if I just look at your specificity, it looks to me like your false positive error rate is 34%, almost 35%. The Kiesler study, he initially reported a 0% error rate, then corrected it and said, okay, when I do the confidence interval, it could be as high as 1/3%. But his specificity is only about 80%, right? So that means a false positive rate in the traditional way could be as high as 20%. The Smith study is bad for all kinds of reasons. I'm embarrassed for the firearms and toolmarks community. They keep putting it on slides. It's got several letters to the editor, even by the author, of mistakes he made in the math. He claims that it's an open set study, but it's really closed set. But even if we set all that aside, his specificity is a catastrophically low 22.8%, which means the false positive error rate, the traditional way, would be as high as 77%. You'd be better off guessing, right? The Ames-2, same thing. They report this around 1% false positive rate. But if you do it the traditional way, it's as high as 66% for bullets and 51% for cartridge cases. And the Guel study, very similar to the Ames-1 study, he reports, less than 1% error rate, but how you handle the inconclusives could bump it up to 36%. So the FDA has handled this problem. We're not the only people who deal with diagnostic accuracy, right? They're constantly having someone say, hey, I've got a COVID detection thing, or a strep throat detection, or a pregnancy detection. And so this FDA guidance document, I think it's guidance document number 19, says you may not ignore these equivocal or ambivalent results. And so they give several ways of dealing with it, but one way is to let the firearms and toolmarks community have their way and say, okay, first, pretend that all of the inconclusive results were really eliminations, and then pretend that all of those results were actually called matches, and you'll get two extremes. And if you do, and then you pick the midpoint, you go, okay, so based on the Ames-1 study, the FDA would say, hey, your error rate looks like it's about, false positive error rate looks like it's about 17.58%, but that's plus or minus 17%. So yes, it could be as low as 1%, but it could be as high as 34%. It's probably neither of those extremes. It's somewhere in there. Same thing with the Kiesler study. You apply the FDA guidance, which I think is a really reasonable way to go, right? This isn't something that some judge imposed. It's how we do this in the rest of science. It's the bar that every other diagnostic tool would have to jump over. So Kiesler, it's 13.6%, but could be as low as kind of 1%, could be as high as 26%. The FBI studies, 33 plus or minus 32, 26 plus or minus 25, right? So that's the debate, is the error rate's probably in, I'm certain that it's in there, but am I certain that it's as low? as the examiners are saying? Probably not. Is it as high as their chief critics would say that every one of those is an error? Probably not. But is it in here and is it higher than they think it is? Yeah, probably. Okay, so we talked about so I said in my mind there's sort of four studies, Ames 1, Ames 2, Kiesler, and Giel. There's a lot more studies on there. If you just look at the dates of those studies, many of those are pre-PCAST, right? So this seems like we're not listening very well. When you have a really, scholarly body say, hey, we looked at these and we think several of these papers are just don't say what we think they say. I think we look pretty stubborn and a little ignorant when we insist on representing those. Is look at all these great studies. Just a reminder, those closed set studies come with instructions like you got 15 sets, but at least one bullet from each barrel, and there's no more than 3 bullets from any one barrel. And so you get these kind of like crossword instructions that say, once you know something about question set G, it might affect what you do with question set B. We did some math around that. I'm going to jump through this, but it's the idea of if I just said, guess whether these cards are black or red, I had them turned over. It's like the chances of getting them all right are 1 in 1,000, 1 in 1,024. If I told you before you started that 5 were red and 5 were black, now the chances are like 1 in 252, right? Of just guessing correctly. So I've just, with that little instruction, I made the test 4 times easier. There's also a debate of examiners. If you go back to that chart of all the studies they put up there, they all claim that there's some sort of blind. And I'd offer to you that they're not any sort of blind at all. So blind and double blind really talks about clinical trials where does the patient know they're getting the drug or a placebo, and then does the doctor and their caretaking team know whether it's the drug or a placebo? That's blind and double blind. What we want in forensic science is something that we almost can't have, this test blind. And that is the examiners sitting at their desk and they don't know whether or not this is a real crime scene sample or is it Nobles has done a lot of these black box studies or is it from Nobles, right? And so for lots of reasons, that kind of blind testing is almost impossible. The Houston Forensic Science Center has done it within their lab. Peter Stout, the lab director there, is amazing and really forward-leaning, but would be really hard, probably impossible to do nationwide. Okay, then there's a few other weaknesses. So this is a paper by Cuellar. She used to work with me at CSAFE, and a few other Rosenblum out of Johns Hopkins. It was published in Law, Probability, and Risk. And so they talk about what they call flaws. I call them inherent weaknesses because this is where I feel like even if you gave me lots and lots of money, these would be hard problems to fix. So they don't render the studies invalid, but they do change the confidence intervals. So if I say, hey, I measured a 5% interval, the next thing any scientist would ask me is 5% plus or minus what? And so Rosenblum does some calculations in the paper and says, even if you get rid of the inconclusive debate, just these other limiting flaws mean that the upper bound of any confidence interval is probably as high as 18%. So that would be like by his estimation, like 9% plus or minus 8% kind of thing. All right, so what I encourage farms and tool marks examiners to do would be to say, here's the studies and the list, like here are the post-PCAST studies. Don't report 0 error rates. Don't ignore this inconclusive. At least exclude it from your calculation and then maybe mention, look, there's a debate about this. They should be transparent about that. They should talk about all those shared weaknesses we just talked about and talk about how that widens the confidence interval.
You want to think
I love that dress.
And then there's also some real challenges with reproducibility in these studies. Finally, they could say, look, here are the preliminary PCAST studies, pre-PCAST studies. They don't have to make those go away, but they should say, look, this shows a commitment to research, but they were set up where we can't really calculate error rates. They have really small sample sizes, participant sizes. And so that should just be shown to say, look, we were thinking about research before we started doing it right. So Marissa, I noticed we're about at the hour. there's probably another chunk here that I don't want to rush through. And so this is probably a good place to break. I'll just highlight there are studies that get left off of there. So like the CTS from 1923 proficiency testing, I don't think those make great error rate studies, but they had a kind of alarmingly high false positive incidence in that study.
Mhm.
And so the way they handle that is by kind of not talking about it at all, right? And I feel like that's where we need to lean in. And the
So it
other
seems
one,
just like a lot of the things you're talking about right now, these are things that people should be talking with their expert about in terms of
absolutely.
review. Okay, like
Yeah,
reviewing these studies. How do
absolutely.
you feel about these studies and kind of giving some
Yeah,
guidance in terms of,
yeah,
yeah.
absolutely, Marissa. But where I would love to see it, right, as a member of this forensic science community is yes, any attorney that's advocating should find an expert to help them talk about these things. But what we really want, right, are that the practitioners are embracing these things. Like
Right.
this isn't advocacy in my mind, right? This is just simple, straightforward science. And so they need to be much more open about this. This is where we don't want to be rhetorical. We're not trying to win an argument as a scientist. We're trying to be honest about what the data show. And I think we fall short there in several forensic science disciplines. So, and then the final thing that would be worth talking about, but once again, this could be its own whole hour, is how often, so Ames 2, they did a great thing. They said, how often did you agree with even your own self? Like 2 weeks later, 3 weeks later, I send you back the sample. And then how often did you agree with other examiners? And that agreement's not that good. And so without understanding the slide, the authors said, hey, random guessing would sort of be on this diagonal line, and look how good we are, we're above the diagonal line. But real scientists come in and go, no, the line that we use is this kappa 0.8 line, and good is above that line. If you're doing real science, good is above that
Wow.
line. So I show you that as a cartoon without offering you the math behind it. But it frustrates me in that there's really smart authors in that Ames 2 study, but that they would offer that seems disingenuous. That they would, come on, guys, you know what a kappa is. You know how to present this in a more honest way. The Abruquata out of Maryland tried to say we can play with these numbers a whole bunch. And so once again, just offered to you as a cartoon, even in the paper, Monson correctly goes, hey, the diagonal is what we're interested in. The numbers should be in the diagonal. And so really you would want it to look like this. But since we know ground truth, this is what it should look like. All the eliminations were called eliminations.
Right.
And so I'd suggest to you that when dissenting justices say, but see, doesn't this make sense? Any scientist would go, no, that's a hot chocolate mess. It should certainly look like the top one, and ideally it should look like the bottom one. That's absurd on the right side. So that's our journey. I realize I rushed through that last part. That could
That's
be
okay. There is a question in the chat, and we get this a lot actually, about the use of 3D microscopy tools like the Evo Finder. Are there any studies that look specifically at the use of that in terms of whether, I'm guessing, Andrew, whether it itself is a reliable, accurate procedure? And then do you have any thoughts on the ability of these kinds of tools to promote greater rigor and validity in this scientific endeavor?
Yeah, that's a wonderful question. So yes, I think that's a great step forward, right? Because now we've got three-dimensional information. That's even better. And you also have it, you're not relying on just a photograph that might be taken with bad lighting. You now have this kind of really rich computer file with all kinds of information about what you saw. Unfortunately, they're expensive. Not very many labs have them. And the ones that do, like at the FBI, that's how they collect their samples now. But it's a little bit like having a sailboat and then taking the sail out and using it as an oar and rowing with it instead of letting the wind blow you. They get that digital information and then they render it visually and still just look at it with their eyes and then still employ the AFTI theory of identification. CSAFE and a few others are currently working on some tools. The CSAFE tool goes by the name Bullet Analyzer. It'll be open source and available to all these vendors. That very similar to the orange and blue line I drew for you said, let's compare these striations mathematically. They use a much more sophisticated machine learning AI kind of random forest algorithm and say, what is that more sophisticated statistical analysis tell you about whether or not this is same source? So you would get sort of a similarity score, and then you get some sort of probability statement that says the probability of observing this amount of similarity, if they were in fact not matching, is less than 1 in 10,000 or less than 1 in 100,000, right? And so that's where we're headed. It's not quite ready for prime time, but there are some really smart people at CSAFE working on that and a few other places as well.
Okay.
So I think I'm hopeful that we'll head there. It just won't be next year.
Okay. And I'm going to go ahead and launch our training evaluation, but in the meantime, there was a question in the chat. What was the CZ firearms study?
The CTS firearms study. So really good question. Is CTS Collaborative Testing Service is one of the main vendors who provides proficiency testing samples to forensic examiners in all things: DNA, firearms and tool marks, fingerprints. And the great team there. They're very forward-leaning. And so they did the proficiency testing that they did in 2023 had an anomalous result where they had way more inaccuracies than they were expecting. It turned out to be a much harder sample. So I'm torn because I don't believe that proficiency testing is a good surrogate for validation studies for a couple of reasons. Normally it's smaller sample sizes, but also the lawyers out there are not going to like when I say this. I would like proficiency testing to not be discoverable. And the reason I want that is because as a lab director, it's like I don't want to. There's pressure on CTS right now. They actually testified or presented at the National Commission of Forensic Science. There's pressure from lab directors of, you can't make these too hard. I can't have my examiners failing proficiency tests and then getting impeached. So they make them very, very straightforward. My stepdad's a pilot at Delta. Their check rides every year, they try to kill them. In the simulator, they take what killed the last pilots and throw it at you, have you crash the simulator and go, let's learn from that and let's show you how to do it right. So in my perfect world, proficiency testing would be, I hope the error rates just egregiously high and we learn something from it. But there'd be no way like that would create a lot of tension in the judicial environment. So proficiency tests aren't great. But this one that's supposed to be idealized and easy turned out to have this false positive error rate, I think close to 20%. And so that, the firearms and tool marks community's response was, almost like, how do we begin to try to explain this away? I feel like, well, how about you lean into that? How about you figure out why? Maybe you guys didn't do anything wrong. Maybe that those CZ firearms are really hard. Maybe that's the right answer. Maybe that the false positive rate for that gun is 20%. So, but back to my very first slide, when you're ingrained with the AFTI theory of ID, you feel like you're a heretic. You can't say that. You can't go, maybe it doesn't work on this gun very well. Right.
Okay. And thank you for that. And I'll pause here to see if there are any other questions. But while we are, we'll remind people of our upcoming other webinars. We have in January, we'll be back with serology and early DNA platforms with Dr. Anjali Ranadiv. We'll be talking about how to interpret or how to read those testings. And Adina is on. If I said that incorrectly, please correct me for that. In February, we'll be working on a case study from Indiana, which was a collaborative effort between the Marion County Conviction Integrity Unit and the Notre Dame Exoneration Project. And then in March, something which has been in the news lately about detecting fraud in post-conviction investigations and how conviction integrity units and innocence organizations can be aware of that issue and potentially not succumb to fraudulent applications or fraudulent evidence that's being produced. So I'm looking in the chat, not seeing any additional questions. So Dr. Salyards, thank you so much for your time for these last 2 months. We are so grateful to you for your time, for helping us walk through this. And we look forward to seeing everybody next month. I hope you have a restful holiday season. And again, Dr. Salyards, thank you so much for your time.
Thank you so much. It was an honor to be here. Appreciate it.
Thank you. Thank you all.